Hi there, team, and welcome to another episode in the Geology 101 Physical Geology video series. I'm Geology Professor Shawn Willsey. Thanks for joining me today. Our episode today, episode 15, is on the sedimentary rocks. So we're going to go a little further into a new group of rocks and some of the processes that deposit and create these types of rocks. This video series, Geology 101, is based on my college course I teach. It's the same curriculum, the same content. The only thing missing, of course, are the hands-on components, the field trips and the labs, but I'll make sure I put some video links in the description here, and you can supplement what you see here with some other videos that show the rocks in a little bit more detail, some hands-on type of activities that you might want to take part in. So let's go ahead and get right to it with this episode. So we've spent time looking at the igneous rocks and volcanoes and how those form. Our last episode was on weathering, which is taking any existing rock, breaking it down into sediment in place. Once the rock is broken down into small enough particles, it can be transported by various mechanisms. We call that erosion. Could be ice or wind or water. And then it is then deposited. So that sediment, once it's moving, doesn't move forever. At some point it comes to rest, and that's what's known as deposition, that sediment that finally comes to rest in some location. So once we have that material deposited as sediment, it can then be turned into rock. It can be lithified through compaction and cementation, and then it becomes sedimentary rock. And sedimentary rocks are the things we're going to be looking at today. They cover a good portion of the Earth's surface. Most of the things you see outside just wandering around are most likely sediments or sedimentary rocks. They provide and create some iconic and majestic landscapes. I think about the national parks in southern Utah, other parts of the western U.S., and other places as well. There's just some fantastic landscapes created by sedimentary rocks. Unlike the igneous rocks, the sedimentary rocks actually provide us a lot more information about what was going on in the past. Fundamentally, igneous rocks just tell you there was magma here, or there was a volcano here, and we can glean more than that. We can tell how quickly it cooled, its chemistry a little bit, but it doesn't tell you much about what's happening at the surface or what's happening with life. But sedimentary rocks oftentimes contain fossils, which tells us a lot about what life forms were present on planet Earth at that time. They also can provide clues about the environment, maybe the climate, which way the wind was blowing, where the rivers were coming from, where they were going to, where the lake existed. They really allow us to reconstruct a good sort of model or idea of exactly what the landscape looked like at the time those sediments were deposited. And then lastly here, sediments are important because they are the host for a variety of natural resources that we use in our modern way of life. So different types of energy resources, some metals, these are all part of the resources found in sedimentary rocks. So let's look at the actual process that allows sediments to turn into rock. So we've talked about weathering and erosion to some degree. Once that sediment or those particles, could be rock fragments, could be other material like shells or other chemical material. Once that material's moving, it can become then deposited. So it's laid down and sits in place without moving, and then it can become buried under more sediment above, and that will cause the material to compact. The particles get closer together, and then the spaces in between. We still don't have rock at this point. We basically just squeezed the sediment and compacted it, but we don't really have it turn into rock until we have usually groundwater moving through these sediments and precipitating out some sort of cement between the grains that allows the grains to become cemented together. So at this point now we have turned our sediments into actually rock, and these two processes combined are what we call lithification, turning the sediment into rock. So the story of sedimentary rocks, the thing that we're trying to entice out of our analysis and description of sedimentary rocks is figuring out exactly the environment in which that sediment was deposited. And this is what's known as a depositional environment. So it's not a specific location like, the east coast of South Florida. It's actually a geographic setting. It could be a beach, could be the delta of a river, could be sand dunes, could be offshore reefs, glacial environments. We're trying to use the clues that the rock has left behind to deduce exactly what that environment was. And that may change from one location to the next as we move across the landscape, but collectively we can put together all the environments that might have existed at that time. So this is really what we're trying to get out of our sedimentary rocks. Yes, we want to describe them. Yes, we want to identify them with a specific name, but ultimately we're trying to figure out exactly how those sediments came to be and in what environment they were deposited in. So you'll hear this term a lot as we talk about sedimentary rocks, the depositional environment. This is the goal. This is what you're trying to figure out when you describe and look at these rocks. So let's start with just some simple terms we might use to describe sediment sizes. And again, this is the Geology 101 level. You actually can get much deeper in the weeds with this. So if you take a sedimentology class, you'll learn about granules and pebbles and cobbles, and there's a whole array of terms that describe sediment sizes. But at this level, I like to keep it pretty simple. So anything over about 2 millimeters, we're going to call gravel. I think that's a size people readily understand and have some experience with. Anything from about a 1/16 of a millimeter on up to 2 millimeters, that's sand. We'll mainly be able to tell sand apart just by its feel, its tactile feel. Rocks that have mostly sand in them will be gritty. It'll feel like sandpaper. And then all the particle sizes smaller than that, we're going to lump that together and call that all mud. It actually includes both silt and clay, but we're just going to collectively use this term mud to refer to this size sediment. So the rocks will tend to feel much smoother. Probably can't pick out the individual grains with your eye because they're too small, but we broadly can classify our sediment sizes into one of these three groupings here. The other thing we're going to look at that's going to provide clues as we do our detective work here with the sedimentary rocks is we're going to look at the shape of those grains. What is the shape of the sediment? Is it angular? Does it have a lot of corners and sharp little points to it? And it might be more spherical like we see on the top here, or it could be more elongated. So the overall shape's not as important as what we actually see looking kind of at the surface. At the other end of the spectrum, we have very rounded sediment. It has no real angular corners. All the surface is very smooth. And what this implies and what this tells us is that these particles have collided. Whatever the mechanism of transport was, whether it was moving water, water at a beach, maybe the wind, that the particles have been banging into each other, colliding, and the more frequent those collisions become, the more we can chip away these little sharp corners and little edges here, and over time make the sediment more rounded. So realize we use a variety of terms to describe sediment shape, from angular to subangular to subrounded to rounded. It's also entirely possible that within one rock you have a variety of shapes. So it doesn't always have to be one. You might have a rock that has both angular particles, or what we're going to call clasts, and it could also contain rounded. It could contain all four of these different shapes here, just depending on the exact history and sequence of events that have led to that rock and those sediments being deposited. So rounding is something we're going to pay attention to. We're also going to pay attention to how the sizes are distributed, what we call sorting. So do we have sediment that's all pretty much one size? If so, we're going to call that a well sorted, or maybe even a very well sorted sediment or sedimentary rock. Or do we have at the other end of the spectrum a whole host of sizes, a big size range and diversity in the particles? Do we see big ones and little ones all mixed together with everything in between? If so, that would be a poorly sorted sediment. And so this is a nice little graphic here that kind of lets you analyze your rocks and come up with this adjective or this descriptor. But more importantly, what this is this is giving us a clue as to what the depositional environment might be for our particular rock. So sorting is important as we look at sedimentary rocks. And in general, we have just two main types of sedimentary rocks. We have sedimentary rocks that are composed of broken rock fragments, pieces of sediment that have broken from older existing rocks. We call these rocks the clastic, or sometimes they're called the detrital sedimentary rocks. I prefer the term clastic, so that's the one I'm going to use, but they're essentially synonymous. And these rocks we're going to mainly sort of divide into groupings based on how big those particles or those broken rock fragments are. And then the other group of sedimentary rocks we'll spend some time with are the biochemical sedimentary rocks. Rocks that form either by the accumulation of biologic remains, could be shells, could be plant material, or it could be the chemical precipitation material that's come out of solution and crystallized into some sort of rock. So these are the biochemical sedimentary rocks, and we're mainly going to divide those up based on composition. What are they made out of? So let's go ahead and just get through these rock names. Now realize, of course, that at higher levels of geology, there's more rock names than this. So this is by no means the all-inclusive list of sedimentary rocks. This is just the ones that the students in the 101 class learn and are able to have some experience with. So this is a very fundamental level, but a good place to start. So we know that the classic sedimentary rocks are classified by the size of the particles, the class or the grains. So let's start with the largest size, so gravel. So if we have a rock predominantly made out of gravel, and those particles of gravel are rounded, the rock name we give that is a conglomerate. So I've got some photos in here to just kind of help you visualize what these might look like. So this is a nice classic conglomerate. You can see that most of the particles are rounded. There might be one or two in there that are somewhat angular, but by and large, the rounding of the class is the most dominant characteristic you see there. Well, what if we have the same thing, gravel-sized particles, but now we have angular particles in this rock? So the term we use here, it's an Italian word, and I pronounce it breccia. Like you could call it breccia. I don't know how it's pronounced in Italian, but most folks I know call it breccia here in the US. And so here you see, again, gravel-sized particles, large enough to see with the naked eye, over 2 millimeters. But here, all of these particles tend to be quite angular, sharp edges and points, corners to the particles. So there's two of our rock names here for the classic rocks. If our main grain size is sand, we're going to call it a sandstone. Pretty simple. There actually are several different types of sandstone, but at the 101 level, we don't dive too far into that minutia. I save that for my historical geology class. So anything that's sand dominated by sand-sized grains is a sandstone. You'll be able to tell that usually by feeling, not just looking at the rock, but feeling it. It should feel gritty and a little bit coarse like sandpaper. As we move down to smaller grain sizes, if we look at particles of mud, and the rock tends to split into layers, the depositional layers that form the rock, we will call these types of rocks shale. So these are dominantly mud-sized particles. It'll feel smooth to the touch, and because it breaks into these little sheets or wafers or chips, this is what we call shale. If it's the same size particle but it is more blocky, we might call that a mudstone. So now it's not breaking along those lines because of its depositional history, but it's still fine-grained, smooth to the touch, and so we would call that a mudstone. So 5 classic sedimentary rocks here to learn in the Geology 101 class. As we move to the biochemical rocks, there's essentially 3, but I do have them learn some of the different types of each, so it's a little bit longer list than just 3. So these, remember, are classified by composition. What are they made out of? And so the first mineral we're going to look at as a component of a biochemical sedimentary rock is calcite. Remember, calcite has the unique property that we learned about with minerals, that when you put a drop of dilute hydrochloric acid on it, it fizzes, it reacts to the acid, and it effervesces. And so that's going to be a big test that folks use in a lab or field setting to see if they have a limestone. If you hit the rock with acid and the whole thing fizzes, that tells you it's dominantly made out of calcite. So a rock, a sedimentary rock that's totally made out of calcite is a limestone. There's many different types of limestone, but we learned just micrite, coquina, and chalk. Chalk is kind of a white powdery rock. Coquina, it's very fine-grained. Coquina is what the photo is here, like it's made out of shells and shell fragments, usually in a offshore reef environment, somewhat near the coast. And then a micrite can be a lot of different colors, but it's going to be more fine-grained and much more resistant than chalk. It's not going to be as powdery. It's going to be harder. This is more of a typical limestone that you might see, as opposed to these two, which are maybe a little bit more rare, but pretty easy to identify. So another biochemical sedimentary rock we have is one in which it's totally made out of silica. Remember, silica is what makes up minerals like quartz. So this is going to be a hard sedimentary rock. In fact, this is going to be a very resistant type of rock, and this is what's known as chert. Chert also has this property of having, it breaks along these little curved planes, what we call conchoidal fracture. And chert, you might know, was used by native indigenous people to create spear points and arrowheads, just like obsidian, so it can be made into tools. And again, it has that, it's very hard and resistant. It's a very tough mineral. So chert is another biochemical sedimentary rock. And then rounding out our list here, if we have plant remains, usually in a swamp, as the plants in the swamp live and then die, they accumulate in the water, but the water is stagnant. There's no movement in the swamp. It's oxygen deprived, and so there's not a lot of decay. And through compaction, you can get that plant material preserved as various grades of coal. And again, there's a whole suite of names that involve, the degrees in which coal has been compacted. But the two we learn at this level are peat, which is a very brown, crumbly, earthy. You can actually see the remains of the twigs and leaves sometimes in the material. You might be familiar with peat moss, which you can get at your local nursery. And then the other type that's shown in the photo here is bituminous coal. So this is the black, sooty, brittle, somewhat lightweight form of coal. In places, this is what's used to generate energy or burn for heating. So this is another type of coal here. So these three are actually pretty easy to tell apart if you think about it. One reacts to the acid, one is very hard and resistant, and one is very dark colored and kind of lightweight because it's made out of these squished plants. So these are the biochemical sedimentary rocks we learn at the 101 level. And how do we interpret all these rocks? Well, ultimately, again, we're trying to get to the depositional environment, exactly how the rock formed and in what sort of setting those sediments came to rest. In general, if we jump down here to this diagram, we can think about the relationship between the sediment size and the energy it takes to move those particles. So larger particles, like let's say something as big as your fist or a baseball, those take a lot more energy to move. It takes more current in the river. It takes more energy along a shoreline to move particles of that size. And as we go to smaller particles, it becomes easier. The energy required to move the particle decreases. So it doesn't take much energy to move tiny bits of mud. You can have that in a lake. You could have that in a very tranquil environment. So there's a relationship between the size of the sediment or the grain size and the energy required to move that sediment. And that's important because as we consider depositional environments, we want to make sure that the environment that we're interpreting for that rock matches the energy level based on the particle size. So if I had a conglomerate, I would expect to have a high energy or a very fast moving stream system or something like that. So I've got here some different depositional environments. This is not an all-inclusive list. This just gives you some ideas. In general, our depositional environments might be based on land. So they could be terrestrial environments like a river, a sand dune. They could be out in the ocean, marine environments like a reef, deeper ocean environments, or they could be transitional where the land and the ocean meet, like a beach, a delta, something like that. So here's some examples of some high energy environments, some examples of moderate energy and low energy. And notice that these crudely correlate to the grain sizes we talked about. Gravel sized particles would be the main or the largest particles transported in a high energy environment. Sand-sized particles might be dominant in these moderate energy environments. And as we go to low energy environments, the mud-sized particles would be the only particles that would be transported because the energy is very low and we can only move those very small fine-grained components. In general, we can think about this game we play of figuring out depositional environments. It's detective work. We're using all the clues available in the crime scene to figure out exactly what happened. So we might be using grain size. We might be using these things like sedimentary structures, which we don't get into in this class, but things like ripple marks or mud cracks or cross-bedding, and also fossils. So all the evidence that the sedimentary rock gives us, we collectively use all that evidence in order to infer possible depositional environments that is really the story of our sedimentary rock. So this shows just a couple of those here as well. We don't need to go over each one of these, but just different types of depositional environments, streams, swamps, dry lake beds like playa lakes, things that are maybe in the desert, more in the mountains, different types of moving water environments. And again, this is not all inclusive either. These are just showing you a few possible depositional environments ranging from marine to transitional to terrestrial or land-based ones. So if any of these terms you're not familiar with them, it'd probably be a good idea to Google them. I will cover some of them as we get into different processes associated with deserts and glaciers and river systems. So some of these will be covered in future episodes. So what does the grain shape and the sorting tell us in the rocks? Well, we've talked a little bit about this, but I think it's important to put this down in writing and make sure that this makes sense. So the angular particles, when we see mostly angular grains, remember those grains get rounded with collisions. So if they're being moved a significant distance from their source, they're going to tend to get rounded. So if we see angular grains in the rock, that means it wasn't transported very far. Maybe there was a landslide and a section of cliff just slid, a few hundred feet or half a mile down the hill and came to rest. So those particles would likely still be angular. And we know that if they move farther, of course, then they tend to become more rounded. So just looking at the shape of the grain tells us a little bit about the distance traveled. Or it could be with rounded grains, you might not have the particles move very far, but they're getting constantly reworked. And a good example of that would be like the shoreline, like a beach. So let's say a rock falls off a cliff near the beach, and now the waves just keep pounding that. As the waves just come in and break day in and day out over and over and over, that's constantly reworking that sediment. It hasn't moved very far from its original source, but the waves are providing constant and sufficient energy to cause those particles to collide and bang into each other, and so we'd expect to get more rounded grains over time. This is why when you go to a lot of beaches and you look at the sand or maybe the gravel or the boulders in that particular coastline, they'll tend to be quite rounded because they've been constantly reworked by the movement of the water. When we look at sorting, if we look at well-sorted sediment, there's also this relationship here where the longer or the further something gets moved in a system, it tends to be sorted. Nature does a good job, for the most part, of sorting sediment given distance from its original source. This isn't like a 100% rule, but it's a general characteristic we see. And conversely, with poorly sorted sediment, that means you haven't moved it very far from the source, or it's been a pretty short period of transportation or erosion for that sediment. So just some clues we can glean from this game we play with looking at the shape of the grains and then also looking at the sorting of the grains. So the last thing we're going to cover here before we do a couple quiz questions is one of the most common ubiquitous characteristics in sedimentary rocks, and that's the layering that we see. And this is the term we use for the layering that we see in sedimentary rocks is bedding. And so these are individual beds. That's the terminology we use for our sedimentary rocks. And we can see in many instances, because it's hard to maintain energy constant over time. Maybe the river flows slow, then it flows fast. Maybe there's a flood. Maybe the ocean has higher storm surge, maybe there's a tsunami. So the energy levels in these depositional environments can tend to ebb and flow and fluctuate a little bit. And so we get different types of rock that are deposited, and these rocks are deposited in packages in depositional events, and we call those things beds. And lest we think that a bed of rock represents any sort of time interval, we need to throw that idea out of our minds, because you can accumulate a foot or a meter of sediment. That thickness of sediment might take thousands of years out in the deep ocean for that much material, fine-grained material, to accumulate to that depth of a foot, let's say, or a meter. Or conversely, you could have a very high-energy event like a big flood or something that deposits a foot or a meter of sediment instantaneously within a day, let's say. And so there's no real correlation to the thickness of the beds and the time it took to deposit those beds. It really depends on the depositional environment, and it demands that we use some other techniques for figuring out the ages in order to sort of figure out the timeline. But just be aware that this is what we call bedding. And when we get to things like structural geology and deformation, we'll look at ways we can measure the orientation of these beds. Are they horizontal or are they tilted? But we'll get to that in a future episode. So, okay, let's do a couple quiz questions. See if you've been awake, and we'll test your knowledge and learning here. So here's your first question. Here's a photo of a rock. And you got 2 blanks to fill in there, so read through that. If you need to pause the video in order to take a few seconds to figure it out, go ahead. Okay, so let's see if we can fill in the blank here. So we're trying to figure out what kind of rock this is fundamentally in terms of the major types, and then something about the sorting. Well, the first observations I'm making here is it's made out of fairly large particles. Okay, we'll assume this is like a fist-sized rock, so these particles are gravel in terms of their sizes, but then the rest of the material is very small. I can see some little tiny specks in here. It looks like there's a wide range of sizes in the rock. And so the first thing is that the rock is made out of chunks of other rocks. Doesn't look to be made out of organisms or anything like that. So the rock would tend to be clastic, and because we have such a big range of sizes, that would be poor or poorly sorted. So the best answer there was C, clastic sedimentary rock that is poorly sorted. Let's do one more, taking it to the next level with depositional environments. So here's a photo. We have some keys here for scale. So here's an outcrop, kind of looking down on the ground. Got the keys for scale. Make some observations about this rock, and then choose from this list of 6 over here which one of these depositional environments is the most likely that best matches this outcrop. Go ahead and pause the video if you need a little bit more time. Okay, so let's start with some observations here. So right away, the thing I'm seeing is the diversity of sizes. I'm seeing a huge chunk of rock over here on the right, another one over here on the left, smaller stuff in between, maybe fist-sized rocks down to little specks. Looks like the entire unit is made out of fragments of rock, so it's clastic, and I can't see any organisms, no evidence that it's a chemical precipitate or anything like that. When I look at the shape of the grains, there's a lot of them that are somewhat rounded. But then I've got like a little one in here with like a right angle to it, kind of is a little bit more angular. This one's got a little point at the end. There are some angular particles in here as well. So I've got a diversity of shapes, a diversity of sizes, and the most important thing here is I want to think about energy. So I need an environment that can not only transport different shapes of sediment, but can transport large sediment. If that's a set of keys, this particle might right here, and this one, which we can't even see the full extent of, they go off the photo here. These are big. These are maybe basketball size or larger. And so what would be an environment that could transport and then deposit particles of those size? Well, swamps are very tranquil and kind of calm. Not much movement there. They're a low energy environment. Same thing with lakes. They tend to be fairly low energy for the most part, maybe more moderate energy along their shoreline a bit, but mostly low energy. Sand dunes are sort of a moderate energy environment. The only thing you tend to see in sand dunes are sand-sized particles. If we come down to beaches could be something like this, but beaches tend to be well sorted, so I wouldn't expect to see such a diversity of sizes and shapes for a beach setting. Beaches will tend to have more rounded particles and particles of similar sizes. Out in the deep ocean, I wonder how you would get rocks from the land transported out into the deep ocean through normal earth processes. The rivers would take it to the coastline, and then you just don't have enough current or wave action in the ocean to transport those particles out into the deep parts of the ocean. And so the best answer here is glaciers. Glaciers can move rocks of any size. They'll transport whatever shape they are. The glaciers themselves don't really round nor sort the sediment. They just sort of carry everything as it was deposited on the glacier down to the terminus of the glacier, and then those deposits tend to get dropped. So hopefully you enjoyed this episode here on sedimentary rocks. In our next episode, we'll turn to our next group of rocks, which are the metamorphic rocks. If you like the Geology 101 series, make sure you hit like and subscribe. There's ways to donate to the cause. There's the thanks button at the bottom right of the viewer. There's also some links under the video description if you want to donate to this series and geology education in general. But thanks for your time, and we'll see you next time. Take care.